Hi everyone, welcome to the fifth Hangouts on Air for Machine Learning Study Jams. Today we have Sriram with us, who will be helping us with a problem statement. We'll be dissecting it over the whole session, and he'll be giving you a walkthrough of that. Thank you, Sriram, for making it on a weekend and giving the session for all our facilitators and all the participants who are watching this today. Thank you all. In fact, to give you an update about machine learning study jams, so far we have done about 34 events across India, and we have about reached 2,500 people across India. So, which is a huge success for first milestone for us. And thank you all of you for making this happen. So I'll give it to Sriram now, who will take it forward. Thank you.
All right, thanks, Pratyusha. Hi, everyone. My name is Sriram. I'm an engineer working on Google Maps. So today I thought I'll give you a give you a walkthrough of the process involved in building an ML solution. And instead of being a lecture with slides, I thought it would be more hands-on with the Colab. So for those of you who have their laptops out, you can actually go along the Colab as I'm going through. So the link for that is mentioned here, bit.do/dissect-ml. So in this Colab, basically, we'll take as a case study, we'll look at this fashion MNIST dataset. So for those of you who've done an introductory TensorFlow or machine learning course, you might be familiar with the MNIST dataset, which is a dataset consisting of images of digits, and the goal is to classify the image to one of the digits from 0 to 9. So in this, I thought I'll do a slightly different version of that same problem with, it's called fashion MNIST. So the images consists of dresses and accessories, and the goal is to classify what type of dress or accessory it is. Okay. So for those of you who are trying to follow along in the Colab, so once you click on this link, bit.do/dissect-ml, you'll be seeing a screen like this. It'll say, click on Open in Playground. And then once you do that, in order to run the code, so I'm assuming most of you are familiar with Colab, similar to Jupyter Notebooks. So in order to run the code, you need to connect to a runtime. And if you just click on connect, it would require a sign-in from a Google account. So please do that. And then in order to run the code, so as you see, these there are two types of cells or blocks in Colab. One is a text block, which is this one that I'm currently hovering over. And this one is a code block, a code cell. And you can run the code by clicking on this play button on the left. So there are cells which have the code hidden because it's not relevant for today's class. So just clicking on play button should be enough. Similar here. So the first step would be obviously to get the data set. So this is a publicly available data set. I picked one from kaggle.com. So once if you click on this link, you'll get a zip file, unzip it, you should see two CSV files, fashion MNIST train.csv and a test.csv. So these would correspond to the training set and the test set. So once you download, these will be available locally on your laptop. But in order to run the code on Google Cloud in Colab, you need to upload the files. So click on this cell. Now, these files are quite big. So for the purpose of this class, I've already uploaded them. So these are the train set is about 133 MB and the test set is 22 MB. It takes a while, about 15 minutes. So I thought I'll go ahead. Pardon me. So one of the first steps once you gather a data set is to analyze it. And this is a hugely important step. Often many people don't spend enough time on it. First, it gives you an idea of how big the data set is. and to what's the problem at hand. Is it a regression problem? Is it a classification or predicting sequences and so on? And what do the inputs look like? So these kind of informations actually can help figuring out what type of models, what type of devices to use for training and inference, and also sometimes uncover bugs. So for example, it's possible some of the samples don't have a label, or maybe the inputs are corrupt and so on. So super important step. So let's first read the file. So you get so for those of you not familiar with Colab, so pandas is a library that's typically used for data analysis. So you can directly load the CSV files into what are called pandas data frames. And then there are useful library functions. So for example, the describe function here prints out statistics of the data set. So let's see what happens here. So these are the columns. So label is one of them. And then you have pixel 1 to all the way up to 784. So essentially, this data set consists of 28 by 28 pixel images with an associated label with them. And the label basically goes from a minimum of 0 to 9, which means we have 10 classes. So it's a classification problem. And so let's see and again, so one of the important things is the counts of the count fields, which says basically the training set consists of 60,000 examples. And we have labels present for all of them. So let's look at the test set. And then again, test set consists of 10,000. Again, the labels are in the same range. Again, you have pixels values up to 784. All right. So far, so good. So again, the other thing you would want to do is look at the label distribution. So for example, here in this data set, we have labels going from 0 to 9. So which means it's possible that not all classes are represented equally. And we can figure that out by looking at the mean. Pardon me. So the mean basically says it's 4.5, which means that all classes are almost equally represented. Sorry. All right. Sorry, I'm having a sore throat. So pardon me for the coughing. So which means that we don't have a problem of unbalanced data set, which is a common case in case of spam or anomaly detection. So this is a simple problem of a balanced data set and a classification problem. So we'll go ahead and run this cell. So I've defined some useful constants which will be of use later. I'll explain them. So for example, one of them is the rows and columns, which are 28 by 28, and the number of classes, which is 10. All right, so let's again look at whether all the classes are equally represented. Same thing in the test set, so there's no skewness. And so another important step is to actually see what do the samples look like. So let's look at a set of samples for each class. So these are arranged in 2 rows and 5 columns. So label 0, one of the sample images looks like this. So that's kind of like a t-shirt, and you have like pants and then a hoodie, and I'm not familiar what the names are. Some accessories as well. You can see the last one looks like a shoe, a handbag, another shoe but looks more like a sneaker, and so on. So this is what the images look like. The other thing you would want to do is within a class, you want to see what do the different inputs look like. So for example, let's say my class label was 0. And then, right, so these all are supposed to look like class label 0, which, so there is some amount of diversity, right? So the lighting is different. So remember, these are grayscale images, so there's no color information here. And so there is some brightness varies across the different samples. So I've displayed just a few of them. We can look at the other classes as well. See. Hold on. All right. So before we build our first model, I just thought I'll highlight some important points to consider while building it. So in this Colab, I've tried to use the TF Estimator API. This is one of the high-level APIs used for TensorFlow training. And so one of the the benefits of using TF Estimator APIs is, so let's say for this problem you're trying to trying to try out different types of models, starting with some, maybe let's say a linear classifier, right? And so what's changing is only the type of model, the input, output, the predictions of the model are going to remain the same. So the input is going to be an image, the output is going to be a class label, right? So TF Estimator allows you to basically abstract out the input and output specifications and focus only on the writing the model part. So I've written the boilerplate code for feeding the data set into the model, so you can just simply run them. And so quite often, the recommended advice to building ML models is to start simple. So the simplest model you can think of is a linear model, which takes in the pixels of the image and predicts the class probabilities. Also, logits here correspond to unnormalized class probabilities. Think of, so what that means is that the output will be a set of numbers for each class, 0 to 9. And when you normalize them, then it becomes a probability distribution. So for example, let's say if you have, let's say, two classes, let's say 3 classes, and the outputs are 1, 2, and 3 for class, for labels 1, 2, and 3, then then you can normalize them, that is divided by their sum, in which case this is, the sum is 1 plus 2 plus 3, which is 6, and then turn it into a probability distribution. So which means that the probability of is 1 over 6, 2 over 6, and 3 over 6. Right. So there are advantages why we use logits as instead of directly probabilities. So the arithmetic becomes easier. Anyway, so the simplest thing is the linear model. So as you can see, first, the linear model function takes in features. Here they correspond to the input pixels. The labels, again, the labels corresponding to each of the samples, and a mode. So these can be run in either train, eval, or predict mode. We'll come to that later. So, sorry. So we first extract out the pixels from the features. And remember, I think earlier classes we looked at how the neural networks or most ML models can't handle big numbers, and it's important to normalize the inputs into a small range. So one way to do it is to basically convert all the inputs into the 0, 1 range. So if you knew the maximum value that a pixel can take, then dividing a pixel value by that max value will ensure that all your inputs are between 0 and 1. So the max pixel value, again, this you can figure it out by looking at the max value here. So one of the columns has a value 255, so which means that, and there's no other value bigger than this. So which means that we can safely use 255 as our value. All right. All right. Moving on. So as I said, basically the linear model goes from inputs directly to logits. So which is, I said, so you have a linear model. So W times X. X here is the normalized input plus a bias term. And you can use, again, in order to, instead of writing the linear function, you can directly use TF layers API to create a linear layer. And then your predictions, your class label will be an argmax, which means, so let's say your model outputs numbers like 1, 2, 3, 4, and then so which means that in order to, what's the class label that the model predicts is basically the maximum of the outputs, and the probabilities is a softmax over the logits. So here softmax is different from simple normalization. You exponentiate and then you normalize. Again, if you're not too familiar with it, don't worry. It's not so relevant for this class. Right. So for the different modes, you would add slightly different code. So for predict, we have already done. So there's, for a given input, you will predict the probabilities and classes. For training, you would want to compute the loss. Right. So if in earlier classes, you may have seen that for classification problem, the cross entropy loss is a popular choice of loss function. So you would compute the loss and then minimize the loss using an optimizer. So here I'm using the Adam optimizer with a certain learning rate. And then for evaluation, we can measure how accurate the model is for the given batch of inputs by, again, instead of manually adding code that computes the accuracy, we can use the TF metrics API. All right. Okay, so that's so much about the linear model. So let's go ahead and optionally, again, it's always important to debug your models, not just when they go wrong, but even when they go right, to ensure that things are as expected. So again, this is optional. I've not included the logging hooks, but this is something you could do. So let's go ahead and train our linear classifier. So so it spits out some logging statements. So first, it constructs the data set, feeds it, compute takes a batch and keeps feeding it into the model. So here, just to highlight, so our batch size here was chosen as 64 in the constants where we defined, and our num train steps was around 5,000. Again, for the purpose of the class, I've restricted it to 5,000. It's possible if you train longer, the loss gets lower. Yeah, and then once you create, so you write the model function, you can create an estimator this way using the TF estimator API. And then there are useful functions in the API such as train and evaluate and so on. So so this helps you focus only on the model function and leave the rest to TensorFlow. All right, so this, because the data set is quite big, loading it in memory takes a while. So so meanwhile, what we can do is look at yeah. So the other steps, I'll skip ahead while the model is getting trained. Is you want to also see, even when the model is correct or incorrect, you just want to ensure that the predictions look sensible. And when it's going wrong, you want to see where it's actually going wrong. Yeah, so this we'll wait maybe a minute for the model training to start. So the data feeding actually takes more time. So this is quite a simple model. Yeah. So the rest of the class, I just wanted to highlight that we will first analyze where the linear model doesn't do well, and then we can try to see if we can improve it. And the other thing, even before trying the next one, where I've highlighted a convolutional neural network, is to actually see if a feed-forward multi-layer neural network can actually do better. All right, so training is going on now. So TensorFlow basically prints out the loss and the step. So for every 100 steps or so, it prints out the loss. So one of the crucial things you want to do while ensuring training is going right is the loss should go down over time. So you might see a slight fluctuations. So for example, it went from 0.79 to 89. So such small fluctuations are okay usually. One of the reasons could be that the batch size is either too small, so or the learning rate is a little too high, in which case it's possible that the batch that was sampled, the model did a lot worse than the other batch, and so the loss went up. So here, small fluctuations are okay, but overall the trend should be going down, as we can see. So at the end of 4,000 training steps, our loss was 0.5. It started somewhere around 2.4, so which is good. So let's see, we can evaluate now on the train test set. So because, yeah, okay, so the first thing to notice is on the training set, as you can see, the accuracy is about 0.81, which is about 81%, and the test set is around 80.9. So it's totally expected that the accuracy is higher on the train set. In fact, the loss will also be slightly lower because the model has actually seen these samples, right? And on the test set is basically the samples which the model did not get to see. And that's exactly what you want your model to do well on, right? So that's basically what's called generalizing. So it's training on certain number of images and then classifying them into different classes. And then on images that it hasn't seen, the model is trying to predict what class it is. And accuracy on this set is basically what is important, because when you deploy this model in production, you don't get to see the label. So the model has to basically predict the label. And so the better it is on unseen inputs, the more confident you can be that it'll work in production. All right. So we basically ran 100 steps of evaluation. Like at each step, we basically sampled a batch size. You can look at the evaluate function here. Yeah, so that we averaged out over 100 trials. And so we can be reasonably confident this is okay. So you would also, additionally, you might want to compute confidence intervals in order to kind of get a better estimate of how well the model is doing. All right, so 80% you might think is good enough. So remember that if one of the simplest baselines, because there are 10 classes here, you can always either predict the majority class label. So let's say, for example, in your 60,000 samples in your data set, if class 5 occurs slightly more than every other class, then predicting class 5 will already give you a certain amount of accuracy. Now, in this case, it looks like all classes are equally represented. So which means that if you were to predict either the majority or random, you would only be accurate 10% of the time, right? So 80% means that it's better than random. Let's look at where the model is actually getting it incorrect. So here I'm using the predict API. So this function, analyze incorrect, you can check it in the helper functions. So I'm only printing out the predicted class and the actual label and the probabilities for the incorrect ones. We can also look at what do the samples look like. So in general, it looks like it's making some of them wrong across all classes. It's not like, so one of the things you want to notice is what if all of the images corresponded to one or two classes? Then that can point to the fact that either that class is hard to classify. The pixels look pretty much like another class, or it's possible that that class label occurs very few times, and you may want to reweight that class during training. Right. So which here we're seeing that out of 100 samples, it mispredicted 16 times, so which basically gives it a score of about 84. And these are mostly distributed across all the 9 classes, so it's not like the model is favoring one class over another. We can also see, for example, let's say the first one, the predicted class was 6, the actual label was 2. So remember, indices go from 0 to 9. So which means, so it did put 0.34 probability to class 2. However, it put 0.357 to class 6. So even when it got wrong, it did predict that the class label class 2 was reasonably likely. However, it wasn't the max. So hence the predicted one was 6 instead of 2. So which means that even when it's going wrong, it's not too bad. Let's look at another one. Here again, 0.31 is the predicted probability of the predicted one, and 0.279 is the probability of the actual one. So which means they're close, right? So if you're familiar with deep learning or neural networks in general, so typically for image-like inputs, there are better architectures than simply using feed-forward layers. And one of them is or rather the most popular one, is the convolutional neural network. Now, in this class, I'm not going to go through what a convolution operation is. You can think of it as, instead of a linear function, it's a different function that's being applied to the inputs. And one of the benefits of this function is that it has some invariant properties. So, for example, translation invariance is one of them. So let's say, for example, I take this image of this shoe and then slightly move it to the right or left by a few pixels. Now, the predictions of the class label hasn't changed, right? So it's the same shoe, but just the pixels have moved, shifted to the right or left by a small amount. Now, typically, feed-forward networks will take longer to get this right, whereas convolutional neural networks, by construction, have this translation invariance. So their prediction won't change if you were to translate the inputs by a certain amount. And instead of trying to go into too much detail, so I'll stop there, and we can actually. One of the drawbacks of convolutional neural network is training, especially on CPUs, is slow. So I'm going to explain how the model looks like while the model gets trained. So this is going to take a while. So we can look at what the model is. How is it different from a linear model? So again, as before, we are extracting the input pixels, but now one of the crucial points about a convolution operation is typically they're applied on spatial inputs, which means you rearrange them in either 2D, 3D, or 1D. And so we're going to rearrange the pixels into a 28 by 28, so the actual image. Remember, in the linear model, we were actually applying it, we were flattening the input. Let's go back. So our inputs here was basically 784 numbers, basically flattened out. And then you have a linear function, so basically a weight times the input pixel value for each of the pixels, and then a bias term in the end. So here, in the case of convolutional neural network, we're going to rearrange the inputs into a 2D image, and then going to apply the convolution operation on the image. And before that, again, you have to normalize the input. So we would divide the inputs by the max pixel value. So again, so here TensorFlow already provides you APIs for using for adding convolutional layers to your model. So there's a tf.layers con2d. So the inputs will be our normalized inputs. Our filters, so So these, think of filters as the number of times you would apply the number of different outputs you would want to get after applying this layer. So what this means is we will have 32 outputs in the end. So the kernel size here refers to the size of the filter. So again, for the sake of time, you can I'm not going to go into the details of convolution, but I would suggest reading up the deep learning textbook. There's a chapter dedicated to convolutional neural networks. And then after applying the convolution operation, you would want to apply a nonlinear function like a ReLU. So I think you might be familiar with ReLU or sigmoid or tanh activation functions. So these are nonlinear activation functions typically used in neural networks. And so they're also popular with convolutional layers as well. And after applying the convolution operation, you apply what is called a pooling operation. So in this case, we are applying the max pooling. So what that means is, so basically a convolution operation, you take a kernel size, a 3x3 matrix, and you stride it across the whole image. Each time, what does striding across an image mean? So you take a 3x3 patch in that image, you do a matrix multiplication, so the kernel matrix, the 3x3, with the pixel values of the 3x3 cropped image, it'll produce a single floating point, right? And then you would collect these floating points basically by striding across. So you move to the next 3x3 patch and apply the same operation. And then, well, after collecting all these floating points from taking one filter and striding it across all the image, you would then take the max of these numbers. So if you notice, this operation basically guarantees or rather results in this translation invariance. So if I move the image of the shoe translated by to the right, then the although the intermediate matrix multiplication outputs would change, the max would still remain the same. And this is what kind of guarantees this kind of invariant properties. Anyway, so we would, this basically, a conv layer followed by a pooling layer is basically what's called a convolutional neural network block. And typically a convolutional neural network consists of many such blocks. So in this case, we have added two such blocks. So two conv layers and two pooling layers. And finally, our predictions. So remember, the output is not, after applying convolution and pooling, is not in the form of a class prediction, right? We would still need to predict, have a logit or a floating point for each class, 0 to 9. So we would then add a linear layer after that. So I've added a dropout layer again. If you ask me how did I come up with this code, so basically this was a slight modification of the MNIST code on the TensorFlow page. So just so that, like, again, if you're not sure where to start, then figuring out what this problem is closest to or very similar to, and looking at the model architectures for that problem is a very good starting point. And yeah, so moving on. So then you have a linear layer, and then the final logits. So the output of the logits layer is basically the number of classes, one floating point number for each. And then the rest of the code is pretty much the same as the linear model one. So I'm not going to, you use the same loss. I'm using, in fact, the same optimizer with the same learning rate. I'm going to train for the same number of steps. So let's see. So again, the loss starts off pretty high, 2.3, but then very quickly goes down quite low. It starts to wobble. So again, it's possible my learning rate is a little too high. I could increase the batch size. But one of the things you can see is that the training time, so basically 100 training steps took 12 seconds. Whereas if you go up, scroll up, and you can see here. So for the linear layer, it was basically a much lesser, right? So all this, the reason is we have more number of weights. The model is bigger, um, and yeah. So the convolution operation is a kind of a CPU heavy operation, and so it's quite natural that you will see a much higher training time for convolutional neural networks. So, and this is one of the reasons why GPUs are popular for training convolutional neural networks, because they're kind of you can tailor the convolution operation or run the convolution operation much faster on GPUs compared to CPUs. Anyway, this is a side note. So again, so this is still training, so the loss is going down. You can see slight wobbles, but it's more or less in the right range. And again, so once training is done, we will evaluate the convolutional neural network on the train and test set again, and then see whether it does better or not. Right. So while training's going on, again, for debugging purpose, what are the things that could go wrong during model training? One is the loss that has to kind of go down over time. If it's not, then there is a problem. Too much fluctuations, again, look at hyperparameters like learning rates, batch sizes. And the other thing is, so let's say you evaluate your model and it's completely getting 100% accuracy on train or test set. Then there are actually, you shouldn't actually declare victory and feel good. It's possible there are actually bugs here. One is, if, for example, let's say the test set accuracy is 100%, then it's possible that the model is being evaluated either on the same set of samples, in the sense that, like, let's say you sample a mini batch, but then the data set hasn't been shuffled properly, so you're kind of getting the same batch, and it's possible that that batch was lucky, in the sense the model was able to do very well on that batch. But if you were to sample another batch, it's possible it does wrong. So anytime you get like either like extreme values like 100% accuracy or 0%, quite likely there are bugs in the input, the model training, or like bugs in the pipeline that generated data. So again, these are important pointers. Training accuracy is always going to be slightly above test because the model has actually seen it. If you see the other way around, again, it's possible there are some bugs in your model training code. But typically, training loss should be lower than test loss, and training accuracy would be slightly higher than test accuracy. All right, so the training is going to be complete soon. Let's wait. What else? Monitoring loss. The other thing you will want to do is with neural networks. Another popular technique is early stopping. So, for example, I could have actually stopped somewhere around 2,500 steps, because the loss is pretty much in the same range now, and in many cases that's actually good, because neural networks are prone to overfitting, and mitigating overfitting either through regularization or early stopping is a good strategy. All right. So our training has completed. Let's look at the evaluation. So again, I'm evaluating both on train and test 100 times. All right, so the accuracy on the training set is about 89%, which is much better than the linear one. So suddenly the convolution network seems to be better than the linear model. On the test set, again, it's close to, again, very close to the training set accuracy. All right. So now, again, we could say, okay, we've done better. We've beaten the linear model. But again, that wouldn't, wouldn't want to stop there. Again, you want to see where the convolutional neural network is making mistakes. So we can see that out of 100 samples, it basically mispredicted on 10 of them. If you look at the distribution of the classes, they seem to be from all 10, more or less. In terms of the actual, so the first image, for example, is really hard. I think even a human would probably make a mistake on that. And again, you would want to look at, even if it has gotten it wrong, what was the probability assigned to the correct class? So let's look at the first one. So it put a probability of 0.18 on class 2 for the first one, and for the class 6 it put 0.74. It was much more sure it was class 6 than 2. So that you could actually again go back and see what the two classes look like. Okay. Right, so this and class 6, yeah. So yeah, the hoodie here, and I don't know what this is, but visually they're not too different. So it's kind of reasonable that the model makes a mistake like that. Again, on the next one, it was 0.11, 0.69. So the other next one, class 5, 0.22 versus 0.7. So it seems to be a little more sure of the wrong class compared to the linear model. Again, you could now see, can I improve this further? And that's quite possible. So again, remember, we stopped training at 4,000 steps. We could go longer or even regularize it a bit more. We could try different optimizers. There's like, in terms of optimizing hyperparameters, that's a different class altogether. But it's certainly possible that we can improve this model even further. Yeah. So basically, the goal of this class was, let's go back to the goals of what today's class was. It was basically just trying out, like writing out the ML model or doing the training is only a small piece of the whole problem. In order to come up with a really good ML model, a lot of the other aspects, like looking at the data set, understanding what it looks like, building a simple model, seeing the failures of that, and then incrementally improving the model is a kind of a good approach to building ML solutions. All right. And then, yeah, so you would want to repeat that. So let's say, when should you stop improving the model? Well, it depends on the product requirement. So let's say if you're satisfied with 95% accuracy, and typically accuracy is in many cases simply precision isn't the only criterion. You would want to also look at recall, like avoiding the number of false positives and so on. So depending on your precision recall requirements, you could either stop saying, okay, I'm happy with the precision recall of this current ML model, and then you can look at productionizing it, or then keep iterating until you get better at both of these metrics. All right. So that concludes the Colab session. So we can do the Q&A. I think let's stop. Yeah.
Yeah, so we have like three questions so far. One is from Manisha. How do you choose kernel size?
Okay, that's a good question. So a kernel size is depends on the size of the image you're dealing with. So in this case, as we saw in our example today, the images were much smaller, 28 by 28. So choosing really large kernel size don't make sense, because remember that the result of a convolution operation followed by pooling is going to result in loss of information, in the sense that let's say the convolution operation followed by pooling detects maybe presence of a whisker. Let's say the images are of cats and so on, right? And so after the max pooling, you lose the information as to where the feature, the pixel values were detected. So the larger the kernel size, you're going to have much more loss in information. So depending on the input size, so there isn't quite a thumb rule as to what a good kernel size is, but typically what you want to look at is um, uh, the number of filters produced and the resultant filter size. So each, after applying a convolution operation, you would get a resultant filter of a certain size. You would want to look at whether that size is reasonably large, even after applying, let's say, 5 blocks of conv layers. So you wouldn't want the kernel size to be such that at the end of, say, 2 layers, the resultant filter size is, let's say, 1 by 1, or maybe even like uh, decreases to 0. Then what that means is you picked too large a kernel size.
In line with that question, there is one more question from Sandia. Can we use transfer learning for such small image sizes?
Again, very good question. So remember that let's say if you're building a product revolving around ML, and let's say your inputs happen to be images. Now, transfer learning is a very good first step, where instead of you training the model against the set of images you have, you could use pre-trained ML models. In fact, they're available on the TensorFlow website as well. Again, these are, some of them will be large. Let's say if you're trying to run them on a mobile device, they won't probably fit. But there are certain other pre-trained models that do. So what you could do is use those pre-trained models, and then try to see if they you would still want to add a linear layer on top. So let's say you take a ImageNet pre-trained model, so which means that this model was trained on images from the ImageNet data set, but you have, let's say, collected images using your phone, for example, right? Let's say hundreds of thousands or thousands of images, not to the order of like 100,000, but much smaller. What you would want to do is use that pre-trained model on these images. Let's say you are trying to predict something. Let's say you're trying to predict maybe what type. Let's say you visited certain places. You want to predict the type of building it is. Maybe it's a museum. Maybe it's a observatory, and so on. So your model, you'll still add a linear layer on top, whose output will correspond to the number of classes you're trying to predict. And but then you will use the outputs of the pre-trained model. So again, it'll be very easy for you to build this ML model. All it requires is just a call to the pre-trained model, and then adding the linear function on top. So this way you can already get a bootstrap from a place where you know that a good con network, how good that is, and then see if you can improve. Yeah.
Okay, there's another question. Ras says that he's confused with pooling layer and he wants to know what it is and why is pooling layer used.
Right. So the pooling operation is basically trying to reduce the dimensionality of the output. So let's say the goal was to detect a white pixel in an image filled with lots of black pixels around. Right. Now, if you apply a pooling operation, a max pooling, for example, then the max will ensure that the wherever the white pixel is, the resultant max value will basically correspond to that. And so think of pooling layer as a way to reduce dimensionality, as well as ensuring that there is translation invariance. So for example, if I were to change the position of the white pixel in the image, if I shift it by to the right or left or up or down, the max wouldn't change. So in terms of how does it help in image classification, so let's say you're trying to build a classifier that's detecting whether there's a cat or not in the image. Then no matter where the cat is, you would want your model to predict, yes, there is a cat. So the pooling layer helps in kind of ensuring that. So just a quick note, if you want to read further about it, I would strongly encourage reading the Deep Learning textbook. It's also available for free as an HTML version. I'll send out some useful links maybe at the end of the class, including the link to the Colab we just went through.
All right, so there's another question. What does the output of convolution layer represent?
So it's just a bunch of floating point numbers. They're called feature detectors, but then again, from the perspective of a neural network, these are just floating point numbers. The pooling, sorry, yeah, I'm not. So you can actually visualize the feature activations. So again, right now I don't have examples of it, but quite often you would see, for example, to detect whether there's a cat in the image or not, you would see activations around the regions of the eyes and face. Like they are much more prominent, like in terms of like a heat map. Compared to the rest of the image. So in some sense, these are like detecting features, like edges, what else? Boundaries, especially. That's also very easy to detect. Yeah. However, a general interpretation is I'm not aware of.
Well, that brings us to the end of this Hangouts on Air session and also the end of Hangouts on Air series that we've been doing for weeks. We hope this session was really helpful to all of you who've been watching these sessions and help you get started with machine learning, TensorFlow, neural networks, and convolutional networks. And if you really like these videos, click the button like and share it with your friends and your community so that even they learn like you did. Thank you again, Sriram, for making this happen. I know you're not well and still you did it. So big thank you to you. And all the people who are watching this session, thanks to all of you for joining in.
Yeah.
Bye.
Thanks. Bye-bye.